So you eloquently explained how we have a long history of blockers that we thought were going to be blockers and we overcame them. But now looking into the future, what do you think might be the blockers? Now that it's clear that agents will be everywhere. So it's obviously we're going to need compute. So what is going to be the blocker for that scaling?
Power is a concern, but it's not the only concern. But that's the reason why we're pushing so hard on extreme co-design so that we can improve the tokens per second per watt orders of magnitude every single year. And so in the last 10 years, Moore's law would have progressed computing about 100 times in the last 10 years. We progressed and scaled up computing by 1,000,000 times in the last 10 years. And so we're going to keep on doing that through extreme co-design. So energy efficiency perf per watt completely affects the revenues of a company. It affects the revenues of a factory. And we're just going to push that to the limit so that we can keep on driving token costs down as fast as we can. Our computer price is going up, but our token generation effectiveness is going up so much faster that token cost is coming down. It's coming down an order of magnitude every year.
So power, that's an interesting one. So the way to try to get around the power blocker is to try to, with the tokens per second per watt, try to make it more and more efficient. Of
Yeah.
course, there's the question of how do we get more power?
We should also get more power.
That's a really complicated one. You've talked about small modular nuclear power plants. There's all kinds of ideas for energy. How much does it keep you up at night? The bottlenecks in the supply chain of AI, like ASML with EUV lithography machines, TSMC with advanced packaging like CoWoS, and SK Hynix with high bandwidth memory.
All the time. And we're working on it all the time. No company in history has ever grown at a scale that we're growing while accelerating that growth. It's incredible.
Yeah.
And it's hard for people to even understand this. In the overall world of AI computing, we're increasing share. And so supply chain, upstream and downstream, are really important to us. I spent a lot of time informing all the CEOs that I work with, what are the dynamics that's going to cause the growth to continue or even accelerate. It's part of the reasons why to the entire right-hand side of me, we're CEOs of practically the entire IT industry upstream and practically the entire infrastructure industry downstream.
Mm-hmm.
And there were several hundred CEOs. And I don't think there's ever been keynotes where several hundred CEOs show up. And part of it is I'm telling them about our business condition now. I'm telling them about the growth drivers in the very near future and what's happening. And I'm also describing where we're going to go next so that they could use all of this information and all of the dynamics that are here to inform how they want to invest. And so I inform them that way like I inform my own employees. And then, of course, then I make trips out to them and make sure that, hey, listen, I want you to know this quarter, this coming year, this next year, these things are going to happen. And if you look at the CEOs of the DRAM industry, the number one DRAM in the world was DDR memory for CPUs in data centers. About 3 years ago, I was able to convince several of the CEOs that even though at the time HBM memory was used quite scarcely, and barely by supercomputers, that this was going to be a mainstream memory for data centers in the future. And at first it sounded ridiculous, but several of the CEOs believed me and decided to invest in building HBM memories. Another memory was rather odd to put into a data center is the low power memories that we use for cell phones. And we wanted them to adapt them for supercomputers in the data center. And they go, cell phone memory for supercomputers?
Mm-hmm.
And I explained to them why. Well, look at these two memories, LPDDR5, HBM4. The volumes are so incredible. All three of them had record years in history, and these are 45-year companies. And so, that's part of my job is to inform and shape, inspire,
So you're not just manifesting the future and maybe inspiring NVIDIA, the different engineers of the company, you're you're manifesting the supply chain of the future. So you're having conversations with TSMC, with ASML,
Upstream, downstream,
upstream, downstream. So that's the thing.
GEV, Caterpillar. Yeah, that's downstream from us.
Yeah.
See? Yeah, there you
Yeah,
go.
the whole thing. I mean, but
Yeah.
there's so much incredibly difficult engineering that happens in the entire semiconductor industry. And it's just feels scary how intricate the supply chain is, how many components there are, but it works somehow.
Exactly. The deep science, the deep engineering, the incredible manufacturing, and so much of the manufacturing is already robotics. But we have a couple of hundred suppliers that contribute the technology that goes into our 1.3 million component rack.
Mhm.
Each rack is 1.5 million components. There are 200 suppliers across the Vera Rubin rack.
So it's interesting that you don't list that as the thing that keeps you up at night in the list of blockers.
But I'm doing all the things necessary to,
Okay.
yeah, see? I can go to sleep because I checked it off. I said, okay, I can go to sleep and I go, well, let's see let's reason about this. What's important for us?
Mhm.
Um, okay, let's reason about this. Because we changed the system architecture from the original DGX1 that you remembered to NVLink 72 rack scale computing.
Mhm.
What does that mean? What does that mean to software? What does that mean to engineering? What does that mean to how we design and test? And what does that mean to the supply chain? Well, one of the things that it meant was we moved supercomputer integration at the data center into supercomputer manufacturing in the supply chain.
Mhm.
If you're doing that, you also have to recognize you're going to move one, and if your total footprint of whatever data center you're going to build, let's say you would like to have, you know, 50 gigawatts of supercomputers that are running simultaneously, and it takes 1 week to manufacture that 50 gigawatts of supercomputers, then each week in the supply chain, the supercomputers are going to need a gigawatt of power. And so we're going to need the supply chain to increase the amount of power it has to build, test, to build and test the supercomputers in the supply chain before I ship it.
Mhm.
Well, NVLink 72 literally builds supercomputers in the supply chain and ships them 2-3 tons at a time per rack. It used to be they used to come in parts, and we used to assemble them inside the data center. But that's impossible now because NVLink 72 is so dense. And so that's an example. And I would have to go into, I fly into the supply chain, go meet my partners, and hey, I said, guess what? So here's what I'm going to do with this is the way we used to build our DGXs. We're going to build them this way. This is going to be so much better because we're going to need them for inference. The market for inference is, coming. The inflection point for inference is coming. It's going to be a big market. And so I first explain to them what's going on, why it's going to happen. And then I ask them to make several $billion of capital investments each. And because they trust me, and I'm very respectful of them, and I give them every opportunity to question me, and I spend time to explain things to people, and I reason about it. I draw them pictures, and I reason about it in first principles. And by the time I'm done with them, there's know what to do.
So it's a lot of it's about relationships and building a shared view of the future.
Yeah.
But do you worry about certain bottlenecks? I mean, what are the biggest bottlenecks in the supply chain? Are you worried about it? ASML's EUV tooling? Are you worried about the packaging, CoWoS packaging of TSMC? About how fast it could scale? Like you said, you're not only growing incredibly fast, you're accelerating in growth. So it feels like everybody in the supply chain, and those are certainly bottlenecks, would have to scale up. Are you having conversations with them? Like, how can you scale
All
this
the time.
faster? Do you worry about it?
No,
Okay.
because I told them what I needed. They understood what I need. They told me what they're going to go do, and I believe what they're going to do.
Interesting.
Yeah.
That's great to hear. So maybe if we can just linger on the power for a little bit, uh, what are your hopes for how to solve the energy problem?
One of the areas, Lex, that that I would love love us to talk about and just get the message out. You know, um, our 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 power grid is designed for the worst case condition with some margin. Well, 99% of the time, we're nowhere near the worst case condition because the worst case condition is a few days in the winter, a few days in the summer, and extreme weather. Most of the time, we're nowhere near the worst case condition, and we're probably running around, call it 60% of peak. And so 99% of the time, our power grid has excess power and they're just sitting idle. But they have to be there sitting idle because just in case, when the time comes, hospitals have to be powered and, infrastructure has to be powered and airports have to run and so on and so forth. And so the question that I have is whether we could go and help them understand and create contractual agreements and design computer architecture systems, data centers, such that when they need the maximum power for infrastructure in society, that the data centers would get less.
Mhm.
But that's in a very rare instance anyways. And during that time, we either have our backup generators for that little part of it, or we just have our computers shift the workload somewhere else, or we have the computers just run slower. We could degrade our performance, reduce our power consumption, and provide for a slightly longer latency response, when somebody asks for an answer. And so I think that way of using computers, of building data centers, instead of expecting 100% uptime and these contracts that are really, really quite rigorous, it's putting a lot of pressure on the grid to be able to, now they're going to have to increase from their maximum. I just want to use their excess.
Mhm.
It's just sitting there.
Yeah, that's not talked about enough. So what's stopping there? Is it regulation? Is it bureaucracy?
I think it's a throughway problem. It starts with the end customer. The end customer puts requirements on the data centers that they can never not be available. Okay, so that the end customer expects perfection. Now, in order to deliver that perfection, you need a combination of backup generators and your grid power supplier to deliver on perfection. And so everybody's got to have 6 nines. Well, I think first of all, right now we ought to have everybody understand that when the customer asks for these things, you have somebody in your data center operations team disconnected from the CEO. I bet the CEO doesn't know this. I'm going to talk to all the CEOs. The CEOs are probably not paying any attention to the contracts that are being signed. And so everybody wants to sign the best contract, of course. And they go down to the cloud service providers and the two contract negotiators that are, I could just see them now,
Mhm.
negotiating these multi-year contracts. Both sides want, the best contract. As a result, the CSPs then have to go down to the utilities and they expect the 6 nines. And so I think the first thing is just make sure that all of the customers, the CEOs of the customers realize what they're asking for. Now, the second thing is we have to build data centers that gracefully degrade. And so if the utility, if the grid tells us, listen, we're going to have to back you down to about 80%, we're going to say that's no problem at all.
Mhm.
We're just going to move our workload around. We're going to make sure that data is never lost, but we can reduce the computing rate and use less energy. The quality of service degrades a little bit. For the critical workloads, I shift that somewhere else right away, so I don't have that problem. And so, whichever data center still has 100% uptime. And so
How difficult of an engineering problem is that, the smart dynamic allocation of power in the data center?
as soon as you could specify, you could engineer it.
Beautifully put.
So long as it obeys the laws of physics on first principles, I think we're good.
What was the third thing you were mentioning?
So the second thing is the data centers. And the third thing is we need the utilities to also recognize that this is an opportunity.
Mm.
And instead of saying, look, it's going to take me 5 years to increase my grid capability, if you're willing to take power of this level of guarantee, I can make them available for you next month and at this price. And so if utilities also offered more segments of power delivery promises, then I think everybody will figure out what to do with it. Yeah, but there's just way too much waste in the grid right now. We should go after it.